Well, n is the power, right? Yeah. So this doesn't, like, this form doesn't address constants, but the easiest thing to do with constants is, to be honest, you can sort of just ignore them, right? You can try and just leave them there in some sense, right? Because constants don't really affect things, yeah. What I mean by that is, so if we want to find the primitive of this, right?
Can I just make it in that form?
In what form, sir?
Form, so, like if it can be divided by a number.
Yeah.
Can I just leave it?
What's the number?
Well, I'm not saying this exact example.
Yeah.
Like if it was 4/2.
Yeah.
But I just not simplified it.
I mean, yeah, like, why wouldn't you just simplify it, right?
Because I'm lazy.
Yeah. In mathematics, the preferred way of leaving an answer is simplified, rationalized, you know, all those kind of things. So my advice would to always be doing that, yeah. So let's go ahead and look at this. Using the rule now, right? We're increasing the power by 1. Let's leave the constant there. And then, Harry, what's our new power that we've got? 3. And so there's your 6 on 3, right? Plus, again, x squared, 8 on 2 is that new power. So can you leave your answer like this? Well, technically nothing's wrong with it, but it's definitely not the best form that we can keep it in, right? If we simplify it out, we get 2x cubed plus 4x squared, and I've forgotten my plus c up here. So again, always making sure to check, is it going to work based off, yeah, are we taking derivatives here? Boom, 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 bada bing, bada bing. Yeah, that works out. Sorry? This one though, okay, like, you know me, I'm not just going to give you 5 of the same kind of primitives.
You gave us 6.
Huh?
It's the 7th.
It's the 7th. I'm not going to give you 6. Yeah. This one here, why is this one different?
Because she's different. She is different. Why did you make it a she? It's always a she. Have you heard of both?
I'll let you have a think about it.
That's racist.
Okay, so we've had a crack at this one, and we think we've worked out a formula. Now, there is actually a formula for like every kind of different form of these, which is a little bit confusing because I think it's sort of okay to think about it intuitively. The fact that you guys could get it by yourselves works really well. In saying that though, I will give you like a formula. We take this guy, and we're thinking, right, anytime we want to find the primitive, we know we're increasing powers by 1, yeah? But the tricky thing is that we have a just more complex kind of function inside those brackets. So thinking back to when we first looked at find derivatives, this is actually a chain rule. So naturally this is often called like a reverse chain rule, right? So how does this work? Well, if you go back to actually finding derivatives, like for example, let's just take a different example. Y is equal to 2x plus 1 to the 4, right? How did we take the derivative of something like this? Yeah, so what was the rule here? Yep, bring the 4 down. 2x plus 1, keep that the same. Decrease this by 1. We have to do an extra step there. Of the inside, which is 2. So we get 8 outside of 2x plus 1 cubed, right? So that's kind of giving you a bit of a hint about what you need to do to find the primitive of this. We need to kind of address 2 things now. The power here, but also the derivative of the inside, right? That's 2 things we have to kind of address. So if I'm taking this and I want to find its primitive, I'm saying, okay, well, keep this the same, increase the power by 1. But now there's 2 things we need to address. We need to address the fact that I've got this power over here. So 1 over, that would normally be 1 over 5, like we've been doing. But what's the other thing we had to address? We had to address the derivative of the inside. And what is that? What is that? 3. So we have to also multiply by 3 on the denominator, okay? And that's 1 over 15, 3x plus 1 to the power 5. Check that for me, that it works out. Activate my trap card. Okay, now, I want to come back to this formula because Matt and Harry have kind of developed their own one, and it's not bad, but I need to make a revision because you've used f dash of x here, and this actually only works with linear functions.
Yeah.
Okay? You can't just always take the integral and do it that way. So it's not always going to work. The general formula is very similar to what you guys have, actually. It's this. Let's do it over here.
Obviously, when you get someone
So if you have dy dx is equal to, what do we have, like ax plus b to the power n, because this is only for a linear kind of expression, then we can say that the primitive function would be similar to what you guys have. You guys have n plus 1. So we can keep n plus 1 there, but we've just got a, right? Because that's the coefficient of x here. N plus 1. Ax plus b, that stays the same. Remember, our power we increased by 1.
So what if there's like a number on the coefficients?
Well, kind of like with coefficients last time, right? We kind of just left the coefficients there, and they didn't really affect anything too much. They throw you off a little bit, but as long as you kind of treat them separately, you can still approach the questions. Just that you have to do some simplification afterwards. That's how I like to approach it. If there's any coefficients that muck things up, just kind of leave them separate. We'll do another one together, right? We can use this form. Using this form, I guess it's better to write it like this almost. I don't know if that actually helps, but right? So same idea. The primitive, or the antiderivative, would be keeping the original one the same, increase the power by 1. What are we going to put in the denominator there? We have to put not only the new power, but also your derivative of the inside part, or the coefficient that's there, -3 plus c, and that gives us -21 minus 3x plus 1, 7. Okay?